Coil winding. It's a simple process, but precisely winding a coil, that's another story. I've built two versions of this machine before, but they both had limitations. This time, I went all in. Linear rails for smooth motion, a proper lathe chuck for grip, a belt-driven access for speed, a 3.1 gear reduction for power. Everything is built for precision, but does it work? Let's build my most advanced automated coil winder yet and find out. The building blocks of this design are the very familiar 2020 rails used in tons of 3D printer and DIY projects. They are great for these projects due to the use of quick-turn T-nuts allowing for easy assembly of the device. These rails also give the build stability and a metal core to bolt plastic pieces to. I have opted for parts printed out of PETG for the end crossmembers, as well as a support structure for the rotating head, and feed tube for the linear axis. The rotating axis stepper is mounted to a piece of carbon fiber PETG that swivels on the front crossmember to tighten the GT2 pelt on the lathe chuck, while the linear rails belt is tightened by moving the rearmost crossmember with two M6 nuts. Jam nuts are then used to ensure a constant tension is held. The last of the printed parts house all the brains and the user interface. These brains are held in a box tied to the back of the rail, while the UI, off to the left side, is mounted in a swivel box. The steppers used in this build are both of the NEMA 17 family. The one for the rotating axis is a standard one you would find on any 3D printer, while the linear axis one is a shorter version with a reduced torque. The reason for this is that the linear axis floats on a low resistance linear rail with a belt drive, resulting in very little force required to move the linear head. Taking a closer look at the linear axis, we can see the head is two parts, a swivel mounted cone to funnel the magnet wire to the end, and a brass nozzle. This brass nozzle is the same nozzle found on many 3D printers. It's easily swappable for a smaller or larger orifice to accommodate different size magnet wire. My only concern with this is the enamel coating on the wire being scratched off by the nozzle, but further testing will reveal if that's an issue or not. If so, a resin nozzle will be printed to take its place. Moving to the other axis, the rotating head is a lathe chuck designed to go in a power drill. I modified a GT2 pulley to fit over the shaft and hung the lathe chuck on two sealed bearings inside the vertical support structures. Mounting the belt between the two support structures gives an even loading to the bearings, ensuring smooth operation and a chuck that runs true. This is a significant improvement from the previous version's plastic chuck. While it's not a 3D printed part, it has much better holding potential, and the pulleys offer a 3-to-1 gear reduction, increasing torque. Now for the brains of this operation, it's very overkill for this simple project, but I had a few extras laying around, so I opted for an Arduino Mega as the base, and I designed a shield to mount to it as well, making it very simple to repurpose the Arduino later if needed. Now the video sponsor, PCBWay, was given the Gerber files for this board, and in no time at all, I had a packet of shields ready to be soldered and installed onto the Arduinos. These projects are always so much cleaner when you get purpose-built boards like the ones PCBWay provided for this build. For a user interface to communicate to the Arduino, I have chose to go the simple 0.96-inch OLED screen and 3 buttons. These buttons are mounted on a PCB that PCBWay provided for the last coil winder video. I had extras of these, and this was a perfect opportunity to use them up. The UI is all mounted inside of a 3D printed enclosure that will swivel to accommodate various user preferences. The UI cables are then routed to the brain box enclosure, which is sporting the channel logo. This simple box is to move away from the previous build's minimalist style of exposed PCBs and give a more completed look. So we've seen the hardware. Let's take a look at the software now. On screen is the Arduino IDE. I won't bore you with 280 lines of code used to set up variables and deal with the UI of the device. All the magic happens here starting at line 280. We have 3 lines of very important math. These 3 lines match the linear stepper's speed to the max set speed of the rotating head in the code. 287 and 288 set those variables so that each stepper can be ran using the command run, and they both will start and stop together at the desired steps since the runtime has been synced via speed. Line 300 through 310 is all the required code to actually wind the coil. The nested while loops keep winding until all layers have been wound, and the internal while loop runs until each layer has completed its total wrap. The direction variable inverts each layer loop, which flips the direction of the linear stepper. This is the basics of the code used to wind the stepper. I'll break the code down further for anybody that is wondering once the Discord is fully operational, as I'm getting very close on that. From here, I'm going to move into a build montage, and then after that, we're going to watch this coil winder wind a very simple coil. After that, I'm going to move into some closing statements. Overall, I'm very happy with version 3. The enclosed wiring gives it a finished look and protects the PCBs from shorting out. The linear rail is a huge boost to reliability and precision. The bought lathe chuck leaves a bit to be desired, but for $30 I can't complain, and it's more reliable to clamp down on to compared to the printed version. As for future upgrades, I have a few things in mind that I would change, but I feel this winder will last me for a while, at least for the next year of speaker building, if not more. I hope you enjoyed the video. Please like and subscribe if you want to see more awesome content like this. Thank you.